good to be here with you guys today to give me a little warm up here and a feeling for what's going on with my talk here, and I actually get a timing also, so I have kind of a feel for how long. If I get too long-winded or something, I'll be able to know it now. So a lot of these things you've seen before in the past in our various discussions, but hopefully it'll put it into a different perspective here today, so you'll find something that will be useful to you today. So our QRPers is insane. We're going to talk about, just so you know where I'm going, introduction, and then we're going to have my definition of QRP, which I'm going to turn this just a little bit more so I don't have to turn around as much. Ideas for experimentation. I want to talk about some different kinds of things that we can all do as QRPers in our experimentation field. Some ideas, antennas and circuits. I'm going to talk a bit about microcontrollers and how we experiment with those, some of the things we can do. I'll give you some ideas there. And then a little bit about my pickleboard, as you've seen some of these things before, and then we're going to show some applications for it. Our frequency counter, we'll show how that works. A CW keyer that I built, based originally from the pickleboard. DDS signal generator, we'll talk about that some. And we're going to talk about a little bit about the SI570. Programmable PLL signal generator, all built on the pickleboard originally and then ported. And then we'll do a wrap up, just so you can see where we're going there. So, introduction. Who said insanity is doing the same thing over and over and expecting different results? Einstein, supposedly. There's a lot of controversy about that. A lot of people, you can't really find a direct attribution to him, and nobody really knows if he said it or not. I actually have my doubts, but be that as it is. Do you believe it? You've heard it applied to all different situations, right? Economics and politics and everything else, right? And everyone says that, and they always take it as a given. But you believe it. I don't. Okay? Because I think QRPers must do the same things over and over and over again to understand what's really happening. Because there are all kinds of factors that are going on behind. Now, say it like this. You sit down at your rig someday and you make a contact with somebody on the other side of the country. 2 days later, you sit down at the same rig, same power, same antenna, same tuner. Do you expect the results to be the same? No. Well, I thought doing the same thing over and over again means you're insane. You did the same thing and the results weren't the same, right? No, because factors change. That's what our job is, to figure out the factors that are hidden and why it's different. Okay, there's all kinds of experimentation we have to do to understand the complete world, not just the little piece that we're talking about. That's why that statement is so misleading. They say you've done that once, no use trying that again. Well, there are lots of reasons to try it more than once. My definition of QRP. First of all, there's the pure joy of the simplicity. And I'm going to talk about a little different side of it today, but I understand this, and please know that I do. I remember sitting on a field day here with our club here a few years ago at Bill Brisley's house at the high school right behind his house. We were sitting in a little screen tent, okay, and we had a 5-watt station. We had a little antenna, a vertical antenna, perched on the ground just 20 feet away. I had the midnight shift. I was going 12 to 4. Murph was coming back at 4 o'clock to relieve me. And I was there by myself, and I was sitting there tuning the bands, not hearing too much new, back and forth, getting a little chilly, put a little coat that I had found in the back. I was in the shorts. It was a hot day. And just sitting there kind of trying to stay awake, all of a sudden I heard this station start to rise. And it was a guy calling CQ. It was not CQ field day. It was just plain CQ. And I listened. It was a VK station. It was a guy in Australia calling CQ. And I blinked a little bit, wake up a little bit. Is this And so just out of a whim, I said, okay, I'll try it. And I wrote my call out there. Boom, he came right back to me. He was whipping along at about 35 words per minute. I had to really struggle to keep up, just to get awake first of all, and then just to keep up with him. But I had a great chat. We went back and forth 3 or 4 or 5 times before the conditions started to fade again, and all of a sudden he disappeared and he was gone again. But we had a wonder. I will never forget that. And it was a simple little 5-watt station running a simple little antenna sitting out. It's pure joy. And backpackers and people that like to operate on a simple little station, there's nothing wrong with that. I'm not saying anything here that's going to take away from that part of QRP that is pure joy and simplicity. But I also think there's another reason for running QRP, And then this is part of my definition. This isn't really refined very well or whatever. It could be polished more. But QRPers do what they do to understand their world with voluntary limitations to discover how it works. Now, what I'm saying here is that sometimes we run 5 watts because we want to see what 5 watts will do. Well, we'll use a different kind of antenna, we'll use a different kind of experimentation. We're putting a limitation on ourselves because we want to see what we can do with that power. We want to see if we can optimize some other part of our station to make it work. So we're putting limitations, but we're trying to see how our world works. First of all, before I go on, I don't know too many of us that would be willing to take apart our Elecraft K3 and put an experimental circuit into it, right? But if we built a little circuit ourselves, we built a little rig ourselves, we might be willing to do that. We might be able to try out something we've always wanted to try, and that's the reason for simplicity, small little pieces that we've done that we understand, and we try to understand more, but things that we probably wouldn't do if we bought a K3 and just cranked it down to 5 watts to run QRP. So my part of it, or my thing about it, is to use simple equipment, but to do experiments with it, and that's why sometimes you need the real simple equipment. So, there's lots of things you can experiment with antennas. That's not going to be the focus of my talk, but it's certainly a wonderful area to experiment with. Once again, we're limiting ourselves to 5 watts most of the time, so that's one of the things you really want to optimize. You want to find out how different antennas work and how you can get out with different kinds of antennas. That's a very important part of the picture. And it's certainly worthy of a lot of experimentation by QRPers. Next thing is just circuits in general. And I say in general, build something and measure it, okay? There's all kinds of circuits and there's ideas, oh, I went too far. There's circuits that you can find in Experimental Methods for RF Design. That's a great book for that. Find a whole bunch of simple circuits that you can build from scratch on a little piece of PC board with little connect the components on and experiment with them and find out how things work. One of the good projects that you might want to think about is a simple little crystal oscillator. Now this one is just a little bit more, this is the basic crystal oscillators in this part of it, and actually it's just the buffers and things that add on to it just a little bit more, because this is really the front end of a transmitter, okay? With just a couple more things on the end of it, you have a full CW transmitter. But this is a beautiful little oscillator that's really entertaining to try to build and to see how it works. You can hook up a scope to it, you can see how it's oscillating, you can see all these things about it. And it's a great thing to try just to understand how oscillators work. The next thing I'd like to do is to encourage you to get a notebook and to write down what your findings are. Keep track of the experiments that you've done. Keep track of the ideas, things you'd like to try and you haven't had time to do it yet. Keeping track of it in a nice notebook, see what experiments you ran, see what the results are, so that later on you can look back and you can see, oh, I did that. How did I do that? What did that look like? What were the results? You want to make a little hand-drawn schematic in there that what you did, what you tried, what you changed. It's a great thing to make it down in a nice notebook that you can find again. It's a key part of experimenters, okay, is record your findings. Now, another thing that you could experiment with, as long as building it, looking at it with the oscilloscope and so on, but try a circuit simulator. And I have an example, LT Spice, I'm sure most of you, maybe all of you have heard about it, but it's a free product that comes out from Linear Technology. It's absolutely phenomenal. A lot of universities and everything else use it. It's free and it's well supported in the Yahoo group here. It's an excellent, excellent program. It has an excellent way of understanding how circuits work in a little different way. Now here's an example of that same crystal oscillator we just showed in the previous thing that we said we built, okay? And then here we watch it. We watch it start up from scratch and we see after, what, 0.8 milliseconds, it's finally starting, it has enough noise that it makes the oscillator start to go. And then looks like a blur because I didn't expand the time out and I wanted to see the beginning here. But you can expand it out and you can see exactly what that waveform looks like. So, once again, it's a very, very interesting experiment to run to see what it looks like in a simulator. Now, you go back and you compare this waveform to what you see in when you hook your oscilloscope up to it. Which one is right? Do they look the same? Then you stop and think about it. I wonder why. Well, the answer is, of course, the one that you built in the simulator is going to miss parts of it. not going to see stray capacitance. It's not going to see some of the noise and things that you pick up in your own circuit. But one of the things that I know Rick Campbell, my friend out in, teacher out in Portland, used to do with his students is to have them build it and have it simulate and then try to make the two match. Add components to this model, for example, to make it, put the noise into it, and simulate the different parts of it to see how, because the more you understand it, the more you can make those two match, okay? Because they're each going to miss different things. Sometimes you put up a scope on it and you're going to dampen out certain noise that you might see on a simulator that you wouldn't see with your scope. So they're both very, very good tools and they're both useful. You just can't blindly use either one. Some people put it on a simulator, they build it, and they go build a circuit, and they say it doesn't work. Well, they missed something, okay? That's the other part of the project again, is to make sure you understand why. Now, as I said, I just added a couple final amplifiers, some 2N 2222s in parallel, and a low-pass filter on the end, and that's a nice little CW transmitter. It puts out about, goes from -15 to +15. It's about 1.5 watts, okay? It's a nice little CW transmitter. We're going to be talking more about that. But I built this thing and it works great. Without very many parts. I modeled it like this first of all to see how it looked. Built it on a piece of board and it worked the first time. Just like it said. But it's a very nice little example again. It's something you could build and understand how it works. Very similarly, I modeled this, it's a little receiver. This one starts out, instead of having the crystal, I simulated it by putting a little signal generator coming in the front with the same size signal that that little oscillator would have used, but just for simplicity and modeling it. And a couple little stages, a little mixer stage here and a buffer or two, and then an audio amplifier, and out comes this nice audio signal. Okay? Once again, it's very interesting to see what it looks like and then to go ahead and build the circuit and see if it matches. But once again, with a few components and you can see how it works. You can dig in there and find out without having to worry about great big integrated circuits and things. Most people use a LM860, 686. They use an amplifier chip out here instead, and that's very simple to do, and a lot of people do it. But this shows what the inners would be like. If you really want to get down to brass tacks and look at very simple components, then this is a good way of doing it. Now, microcontrollers. When I got back into, I was out of ham radio for a few years around college days and soon after, where I was concentrating on the computers only. And once I got back into it about 1995, my kids dragged me into it, by the way, asked me about it, and it was really fun. But one of the things I was thrilled about is to see how microcontrollers had taken over in so many of the areas and so many things that you could do with microcontrollers that overlapped with what my interests were in ham radio. And I quickly got into some projects using PIC chips and so on, and it was really, because I'd been playing with computers before, it was really fun to see how these things overlapped and the things you could do with a very simple microcontroller. Now, what's a microprocessor versus a microcontroller? You probably heard both terms. Now, I'll give you an example, a Pentium versus a PIC, okay? I'm just saying these are one example of each, okay? Pentium you think is an engine, a very powerful engine, but it has to go off the chip when you get to the peripherals, when you get to the memory, when you get to all the other parts of it. It's an engine that does certain things very, very fast. Versus a PIC. Now, a PIC would have the memory and a lot of those peripherals built into it, okay? So they're all set to go as a little standalone package. The memory is all there. Now, am I saying a PIC is better than a Pentium? Not by any means. I'm just saying they're different, and they each are for different purposes. For a big fancy PC, of course, a Pentium is great, and you can put the other components around it and build a very wonderful computer. And for a PIC, it's for controlling small things, but then it's all self-contained. With just a few extra components, you can do all kinds of control things. So that's basically the difference between the way it gets more complicated than that, but that's a simple way of looking at it. So microcontrollers that we're going to talk about are very cheap. You know, a couple bucks now, typically for a lot of the chips that I work at, the small PICs, and they're very powerful. Now, from that, I'm going to give you a quick story there too. The little PIC that I use in the pickle board, okay, it runs at a 4 megahertz clock and 4 clocks per instruction, so that's 1 microsecond per clock, which is 1 million instructions per second, right? Well, a few years ago, I was consulting down at NASA with the guys at NASA in Houston, and the engineers there were very proud. They have a little mantra that said, "We went to the moon on a MIP and a MEG." 1 million instructions per second, 1 meg of memory, okay? That's the speed of a PIC, okay? Now, they have a little more memory than I have in the standard PIC that I do most of my experiment, but a lot of the PICs have a meg of memory also. So, it was the 286, by the way, they used. It was a hardened 286. There were newer technologies, but they hardened this one and they knew how it worked. That's what they went to the moon with, okay? And you say, we've got that in a $2 PIC now. Okay, so, very cheap, very powerful. Many different types, and I'm not even going to get into the pros and cons of all the different kinds of microcontrollers that are out there. They all have good points. I'm going to talk mostly about the PIC because that's the one I've been using for years because it was one of the early ones that came out. And I've used the other ones in work situations and so on, and they're great also. I'm just saying, once you learn one of them, you can very easily go to another family without too much problem. Okay, it's just a matter of learning the new instruction set and switching over, and it's not difficult at all. The main thing is to understand one of them and get to think about how a microprocessor works. Basics are very simple. Okay, there's a very limited number of instructions that you really have to get to use, and it doesn't take too long before by starting with a program and taking it apart, for example, you can very quickly see how it works and then build on that. And there's various programming languages you could use for it. Now, I've done a lot of my work in assembler, but there are C compilers, some of them are free, and there are basic compilers, and they're all ways of doing it, different ways of doing it in certain applications, certainly in work applications. They very seldom write in assembler anymore because it's so difficult to debug it. Okay, it takes a lot of time to write simple routines, and for a maintenance point of view, usually it's written in C most of the time in a work situation, or C or C++. Okay?
What do they mean when they talk about, when you say compiler, that doesn't generate the code or whatever, does
No,
it?
a compiler is what takes the code that you write in an English type format, whether it's an assembler, you write in a text editor, or in a C or whatever, you write it in the language, and then you push the button and it compiles it. That's making the machine language out of it, okay? Whether it's a compiler or an assembler, there's assemblers that we use. Even when you write an assembler, you still have to compile it to make the machine language that you dump into the PIC itself. Okay, it doesn't know anything about English, it doesn't know anything about letters, it wants numbers, it wants hexadecimal numbers dumped in there. Binary numbers, really. But it wants numbers dumped in there only, and that's what the translation is, whether it's a compiler or assembler. Now, PIC simulator, there's also some really nice PIC simulators out there, and one of them that's free, not free, almost free, 39 euros, about $50. That's excellent simulator that oh boy, it's getting dark now. That I really appreciated. I used it a lot, and I would highly recommend this simulator. You can download a trial version, oceansoft.com, and there's also a support group out there for it. But I have found this to be extremely valuable for understanding how PICs work. Now here's the main screen that opens up when you start the simulator. It shows all the different registers, all the different internal memory locations, what they look like as you run the program. And so you can run it step by step, or you can run it in full bore mode. Okay? And all the different kinds of microprocessors, PICs. There's different versions for different kind of processors, by the way. This one's for PIC only. And this one's for 628 right now, and the clock frequency of 4, but you can use other PICs as well and other clock speeds as well. There's all kinds of tools available. When you hit the tools button, this is the menu that opens up, and there's all kinds of options there that are available to use in the simulator. Once you start running a program, the little microcontroller view is what you see. You can open up and put it on the side of your screen. And this shows all the different registers, or all the different pins that are available on the processor. That's the center part right here. Here's the pins of the and this shows you the name of the different pins. And this shows if they're inputs or outputs, and it shows what the current state is. Now, if the T means it's an input, and you can change it manually to change it from like if you had a keyer coming in and you wanted to change it from a high to a low, you can simulate that by just clicking on that T, and they'll change it from an off to an on, and so on. If you don't see that there, that means it's an output, and it's generating that signal on or off. So this is the main screen of the microcontroller view. We usually put off to the side on your screen. And one of the things I like about this OceanSoft simulator is that it has an LCD, a 2x16 LCD that's simulated automatically. So I can take any of the programs I developed for my pickle, for example, that has a 2x16 LCD, dump it into this simulator and run it without any changes at all. And this is what I see coming out on the screen. I did an awful lot of the debugging for my pickle programs by using this, especially for standalone programs. But it's very nice to see, you know, once I run it on the pickle, this is another way of looking at it instead of running it strictly on the pickle. Now, a little bit about the pickle board itself. I mentioned that back in 2004 is when we first developed this. George Heron, N2APB from the American QRP Club asked me about it, asked me if I'd be willing to work on a board they could run along with a course that they were going to be developing, the Elmer 160 course by John McDonald, right down at WB at RCR. I wanted to make a board that goes along with it so they could teach people, they could run the course and then dump the code into a board so they'd be able to demonstrate how it worked. And so after he asked me, and a couple weeks later I had a kind of a rough sheet drawn out, on a rough diagram drawn out on a piece of paper, and I started prototyping. And I'd make one part of it work, and then because we had so few pins, we had to reuse many of them for many purposes. So it took me a while, but after a couple generations of prototypes, I finally had one that worked. And we ended up selling them through the American QRP Club. We sold probably 1,000 of them before too long. Then I've gone on and generated a couple more additions and made some corrections to it and made some updates to it. Some of the ones that were originally built were using some surplus parts that were available in a batch, and once they ran out, we couldn't get them anymore. For example, a small LCD that we were using. So I had to redo it for parts that were available through a commercial supplier, DigiKey or whatever. And so I ended up changing a lot of it and redesigning it so I could use standard off-the-shelf parts and continue making them. Currently, I run the Pickle 3, and that's still being sold. A lot of people are still buying them all over. And there's a picture of what it looks like. This is with a dollar card, put it in it right here. It's kind of hard to see with the lights here, but and you guys have seen them though, I'm sure. Just a quick, this is what the schematic of the pickle looks like. There are really two halves to it, separated at the little header up there, okay? The left half is the programmer portion of it, and I'll blow it up here a little bit. I don't know if you can see this or not, but this basically has a pick on the outside of it. This is a clone, basically, a simplified clone of the PickKit 2 that Microchip makes. And some simplified, there's some different MOSFETs being used that I changed instead. But it uses a pick with code that they supply, or actually that they publish. And I was able to load that in so I can use their code. And this is kind of the engine that talks to the USB, okay? The original ones had a COM port. It was very simple, but everyone, of course, not everyone has a COM port anymore. They all have a USB, and they all wanted that from the beginning. So this talks to the USB. This generates the signals to talk over across the header to the rest of the programmer. So then the right half again, and the right half is the experimental part of it. All the signals come in there. Once you get down to the pick, then you flip a switch, and from then on, we're able to use all the different components that are part of the pickle board. Now, I was just going to show some of the basic connections that I have, just to show you that how simple a pick really is and how few connections you really need to make it work. It's got just a master clear, it's just tied up to +5 volts. When that's a 0, then it's reset, a ground connection, and a crystal. This one uses a crystal, a 4 megahertz crystal on the pickle board. Some of them you can configure so you don't need that, but the very simple version of it, you use a 4 megahertz crystal with a couple capacitors, tie VDD to +5, and that's basically the connection you need. This says 16F84, by the way. Some of them say 16F628, which is the newer chip that I usually use, but they're all completely the same pins. And this one just shows why you can start the program over by just grounding that MCLR pin through a switch. Now, the basic connection you can see I have 4 push buttons here that are going to different pins on the pickle board. So you can write software and you can be monitoring those pins. So when you push one of those push buttons, you can see it in your program and you can say, ah, that push button 1, 2, 3, or 4 has been pushed. It has 4 LCDs, 3 down here and 1 here. Once again, you see these are on shared pins along with the LCD, and that raises some problems, but usually not. That you can, once again, you program, there's 2 different ways of programming, basically making an LED light. One of them is on the left, which is where you put a high signal on like RA2, or this is an example, of course. You put a high signal here, and the current goes through the diode to ground, okay, and it turns the light on. When you turn the RA2 off, you put a 0 there instead, then the light goes off. The other method of doing it is, actually the method the pickle board uses, is when you source, you sync the current instead of source it. So you put a 0 here, and then the current goes from the 5-volt source down through the LED to light it up. When you put a high here, then no current flows, and then it's off. So either way is possible. It depends on how you want to do it in your circuit. And next thing is CW paddles. I have a couple of paddle connections here that go to pins. If you want to, it's an external jack. If you want to plug in a set of paddles and make a keyer, we'll talk about that in a minute. This is where you connect it up through the paddles jack. Here's another illustration of the same thing with how the paddles work. Basically, they're just grounding that pin. It has a pull-up resistor to +5, so normally when you leave it, it'll be, when you monitor these pins, it'll be +5, it'll be a 1 signal. And when you ground either one of them, then your program will detect that and say, oh, that's a 0 now, and that must be the paddle being pushed, either the DAW or the DIT paddle. The transmitter is over on the right there, and here's a little better diagram of it. So basically, when you set a high on this RB7 pin, it goes and it keys this transistor, 2N2222, the popcorn part of all parts, and through a serial jack, so you plug in a connector to your transmitter, and this will key it. This will turn it on and off in CW. The next thing is a speaker. And this is the first version we did with an RA2. You put a high on RA2, it goes and it turns the transistor on, which causes current to flow through the speaker to ground. And so when you toggle RA2 on and off, boy, it's almost out, it's getting weak here. RA2 is going on and off, that's how you turn it on and off, that's how you hear sounds in your speaker, and the rate that you turn it on and off gives you the tone that you have in your speaker. Now, this one has a little bit of a problem in that if you leave RA2 on, when you go on to another part of your program, you're going to continue to leave that transistor on, and current's going to flow through the speaker, and it's going to get hot. And this is the way we originally did in the first pickle, and then we realized, no, this is kind of a nuisance. So I changed the circuit on the next one to put a blocking capacitor in there. So now all the AC goes through, but transitions go through it just fine. You turn this on and off, it'll go through the capacitor, and it'll still key it on and off. Just that if you go away and leave it as a 1, the capacitor will eventually stop it from heating up your transistor. But for any kind of normal frequencies that we operate, audio, it's just fine. That size capacitor and resistor works just fine, and you hear the audio just like it was before. There's an LCD connection at the bottom. This is the way the pins look in a simplified version. You can see the way they're hooked up. There's the data connections over here, and then the control signals are over here, and these are for the contrast setting for that particular type of LCD. A rotary shaft encoder, this is if you want to tune it for making a tuner type thing. This is the connections, the way they work. Basically, it's got 2 pins that are inputs, and there's a pull-up resistor on each one of them. And the 2 capacitors are just for noise suppression, for debouncing basically. And so as you turn the encoder, you get quadrature signals. You know, they're 90 degrees out of phase. Theoretically, you only need one of them to tell if it's turning or not. But once you have 2 in quadrature, that allows you to tell which direction it's turning. There's a simple little algorithm that you can use to tell if it's going counterclockwise or clockwise, so whether to increment or decrement your frequency. There's also another little connection down here, you see, and this is for the daughter card. We originally set it up for the DDS30 or DDS60 daughter card to plug into that little socket, and later on I actually made my SI570 daughter card to plug into that same socket. So it just got some basic power and connections, power and signals, control signals to go into it to generate RF coming out of a single another pin. And that gets routed in the pickle board back to that output jack. Or in a standalone board, you can run it to whatever jack you want to run it to. Now, another thing that we've done with the pickle board is to make a frequency counter. And this is an example of a little frequency counter I did all in the software in the PIC. Let's see if this works better. This is really getting dim. Oh, that's better. Okay, so all of the code in the PIC is doing this completely. And this is a 10 megahertz frequency standard. And you can see it's reading 9999997. It's 3 hertz off. Oh, darn. But with the kind of counting that I'm doing, I'll show you in a minute, that was with a 4 megahertz clock, that's as close as you can get, is about 3 hertz, 3 to 5 hertz off from the absolute standard. This is the pickle board. You can see where the signal is coming in through a little header into a signal shaper that I'll show you in a minute, and back up and down into RA4 in the PIC. Here's a little different. Basically what we're doing is taking a very weak RF signal. Quite often you don't have enough to really drive the signal levels that we need in the PIC. So this is a little shaper circuit that just basically slams it on and off with a small signal here. It'll make a larger signal coming out of RA4 so that it can be detected properly in the 628 PIC. Now, a basic frequency counter, I'm just going to give you a little bit of operation how it works. If you have a fast enough processor, what you really need, if you start looking at the signal, by the way, this has got a high and a low level, you see. 2 volts and 0.8. So if it's higher than 2, you know it's going to be a 1. If it's less than 0.8, the PIC is going to say it's a 0, okay? There's no man land in between, so you really want to get it above 2 and below 8 to really make sure that you got the proper signals. And so if you could just keep looking at it real often, okay, and every time it goes below the low, okay, you make note of that, and then every time it goes above the high after coming from a low, then you actually make a little increment your counter, okay? So that's the only time you increment your counter is when it's going from a low to a high. You detected both of those, then you know, I got a cycle, okay? And so basically what you have to do is count these, and if you turn on the counter for 1 second, you see how many of these increments you got in 1 second, there's your frequency, okay? And that's a real simple little one that you can do by just, with their basic counting, you can get up to 83 kilohertz or so with a 4 megahertz clock, just by simply clocking it on and off, or watching the clocks without anything other than an RA4, just a simple in-out pin. Now, if you want to go a little faster in frequency, up to like 16 megahertz, for example, with 3 registers, you have to turn this little pin into a counter pin instead, which is just an internal configuration that you do. And it's the same input and everything else, except now you run it a little bit differently. You see, you let the processor count them. You don't have to watch every one. You let this little thing count them for you. And every time it gets the register full, it gives you an interrupt. And you have a certain length of time to handle that interrupt and get back again so it can continue counting before it overflows again. So you're keeping track of them in a different way, but you're letting the fastest part of it go right into the processor itself. He keeps track of most of the counts. And so you can get up to a 60 megahertz count very easily. And that's what that example I had to show 10 megahertz with very simple code. Now a little bit about a CW keyer. I'm just going to show a very simple, once again, this is the orientation, just adding on a couple parts. Okay, you put a capacitor on there just for noise suppression. Put the crystal on there, put a pull-up to the master clear so we don't clear up. There's a push button if you want to restart the program from scratch again. This is a pull-up on another pin. I'll show you why. We're going to have a push button on that particular pin. This is by the way, they're all pickle circuitry. The way it is, I'm showing how it's broken down. There's a push button there that you can detect on RA2. So RA2 can be monitoring this, and you can say, yeah, there's a pull-up, and every time I push the switch, it's going to ground it, so I'll detect a 0 there instead of a 1. Now, there's also a couple pull-ups on RA3 and RA4, and that's where the two more switches, push button 1 and push button 2, are located. The DIT and the DAW and actually have the paddles connected to the same 2 pins. So you can actually push the buttons as alternate instead of, if you don't want to push in the paddles, you can test it out by pushing push button 1 or push button 2 and seeing how your keyer circuitry works without even having paddles connected. And And then it also has a speaker driver. It comes out of the same one as the push button 3. Once again, you use the circuitry with the blocker and everything, but you can, generate a tone if you want a side tone generated by the keyer. This works just fine. You just have to make sure that the switch is turned. When you're ready to generate the tone, you don't have it configured as an input looking at the push button. That's one of the limitations we have because the pins are so used, and this is the way the speaker was hooked up. It was made to use one or the other. And then the output, once again, there's a pin on the pickle board that keys the transmitter. And so there's a complete CW keyer. And I have code out there on my website that shows how to turn the pickle board into a complete CW keyer. It's very useful and works just fine. Now, in 2009, Terry Fletcher, AA0ZZ, asked me if I'd be interested in making a keyer circuit. He asked me to make as a fundraiser for Ozark Con that we just talked about. And so I told him I'd do it, and we ended up developing code over the next couple months and a board, and I ended up coming in with a little keyer that uses 12 direct commands. It's very simple to use. There's no manual to pull out to figure out how it works. 5 to 55 words per minute, ambient A or B, straight key or Cootie key. Cootie key is when you have both the sides of the paddle kind of like straight keys, and you can make did da 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 did just by holding the paddles, closing like a straight key, but it's not iambic. It's not generating the dits and das for you. Sequence line mode, mute line. For some people use that to keep the thump out when you're switching from transmit to receive. It has a little different timing. When you push the paddle, it keys the mute circuit first, and 7 milliseconds later, it actually starts the dits or the das. Same on the release. When you release the paddle, it stops the tone, and then 7 milliseconds later, it actually releases the mute. And some people are finding that very useful when they have separate transmitter receivers and they want to keep the thump out of it. But it has default modes and speeds and everything, all stored in EEPROM. The speed is entered by command or by the paddles, a simple little way of flipping the paddles to change the speed on the fly. And low power is about 1 milliamp when it's active and 1 microamp when it's in sleep mode. So no power switch is even needed. You just flick it when you need it. Current speed is reported 3 to 5 volts, 600 hertz side tone. Auto spacing, you can turn that on or off. You can swap the paddle sides. And key line goes low when it's active, and it's on a little small board. They're currently selling this from the American 4 States QRP Club for $17. It's a simple little kit, and they just gave me an order for another batch of them. They ran out. So, and now I'm going to show you how we morph the one on the pickle into an AZ keyer. First of all, I removed the crystal. How I made it a very simple board. I pulled the crystal out of it, okay, and I got rid of the reset line. Changed the 5 volt to a battery. I stuck it over there. Okay, and I took the speaker and I moved that to another pin. And then I simplified it by getting rid of the resistors. So now you can see it's just simple. Turning RA7 on and off makes the tone in the speaker. There's enough resistance there so it's not overkill, and it works just fine. Once again, this is just getting rid of all the hardware possible. I changed the transmitter keying, moved that to a MOSFET and moved it to a different pin. I'll show you why in a minute. And I took the push buttons and I moved them down to, these 4 pins are ones that can be monitored by the PIC for interrupt on change. Okay, the rest of them can't on a PIC. So what this means is anytime that any one of these lines change from a low to a high, the PIC will be interrupted and it'll start up again. It'll come out of sleep mode. So basically I needed to have, of course, the 2 paddles, and then I wanted 3 push buttons, okay? But these are the only 4 that are available in this kind of mode to bring it out of a sleep. So I had to do some tricks, okay? First of all, I made 3 push buttons on 2 pins, and I did it with a couple of diodes like this, okay? So basically you can push PB1 or PB2, and each one of them has a dedicated line. PB3, when you push that, it pulls both PB1 and PB2, okay? But it still works just fine for messages. So now I can have 3 distinct messages. You push any one of the 3 buttons, and the message from that will go out. And then, of course, I moved the paddles down to the other one to wake it up. So that's how I use those 4 pins, the only ones I really had to wake up on sleep. And that's all I really needed to bring this thing out of, so I could sleep and not have a power on and off button. Changed that to a normal I/O pin. Added a mute. This is the other mute circuit that I talked about that keys off another pin to, if you want to use it. I don't personally use it, but a lot of people like it. And there's basically the AA0ZZ easy keyer. There's the board, what it looks like. Very simple little board, inch or so square. There's with the components mounted on it. It has a little button speaker. It's kind of hard to see here, and that works fine. If you want to expand it a little bit, when you put it together, I just use a little Radio Shack speaker just to give a little more volume, especially when the case is closed. You want a little more volume on it. And that's what it looks like in the packaged form if you want to put the decals on like that. Now, what time did we start here, by the way? Was it
I got your timing, you're at 40 minutes that you've been talking so far.
40 minutes? Okay, I gotta go. Simple little keyer, you know, basic key your timer. The word Paris is often used as a calibration tool because Paris, with the ending spacing, has 50 elements, okay? 50 dit size elements. So at 5 words per minute, you 240 milliseconds per element, and 25 words per minute with the calculation comes out to 48 milliseconds. So you can very quickly see how to run the loops inside your keyer. Now, for a very quick lesson, I'm not going to spend a lot of time, but this shows you if you have with a side tone, you have a basic count that you're going to load based on how fast you're going, and you're going to run through a little loop here to see how long to keep the dit or the DAW on. This is a dit delay. 1 dit delay, it's going to take that count and it's going to run it through this loop this many times. Okay, now it's going to actually generate the tone too, because it has to turn that on and off inside here. And so it has another little count that based on 600 hertz, how many times it'll go through this loop. And then it'll turn the tone back on, turn the tone line on, and run through another little one before it turns it off again. And it's going to loop back again. So it turns it on and off, and the instruction cycle time is just calibrated such that it puts out a 600 hertz clock if you run it this many times through the loop, and each one of those. So, and then if you have no side tone turned on, you want it to still use the same dit count loop, and basically the no-ops are in there instead of the internal loops, and you can loop this instead, and it just doesn't key that tone on and off. But basically, it's very simple code, okay? So keyer doesn't take a lot to get it going. Of course, there's other support things to make it change the speed on the fly and all that kind of thing. But the basic dit and the dit circuitry in PIC is not very hard to understand how it works. There's just a bigger loop in there for just that, and no tone is turned on and off, and it runs that many times. Okay, now the direct digital synthesis, just very briefly, 9854 and 9851 is a very common one that's used in DDS60. Reference clock comes in at like 30 megahertz, and there's a 6 times multiplier in it. And 40 bits come from the PIC, and it generates a signal coming out of the DAC. This just shows how the DDS generally works. There's a whole bunch of little jaggies. It is a lookup table, so it looks at it every so often based on the number you sent it, and it paints this picture. Well, the problem is, of course, every one of those little jaggies causes a little bit of noise on your output. And that's one of the basic drawbacks of a DDS, although they've done all kinds of things to improve that. So this has got this is how the DDS60 looks, and it's plugged into a pickle board here, and you can see how it sits there. 9854 is another project that I did, of course. This one comes out with 2 outputs. It's a slightly different clock speed, and 256 bits go into 9854, and it comes out with 2 signals in quadrature. Basically, you need that for getting sideband suppression and so on. And this is my IQ Pro that used the 9854 in it with 2 picks to drive it. And this was the cover of QEX a couple of years ago. This is actually a prototype board that I etched at home. I guess they like this picture better than the commercial one with the green thing that I finally ended up with, but this was the prototype board that I did it all on. And that's still available at, I still sell a few of those. I sell the key parts for it, and people can get the rest. The SI570 is the one I've been working on lately, and it puts out a nice 1.5 volt peak-to-peak signal. And I'm not going to go through a lot of this, but it comes out with a nice signal that you can generate and run it into a variety of, use it as a signal source for a transmitter or receiver. The advantages, of course, is that much less power, about 90 milliamps versus 450 for a typical DDS. Clean RF, and it's much cheaper. Disadvantage is that the lowest frequency is about 10 megahertz. You have to divide it down if you want to go faster than that. And it's not good for large moves. If you're going to do frequency hopping, if you move a certain number of kilohertz from the center, you've got to stop and let it resynchronize. It takes about 10 milliseconds, so the RF is shut off. So it's not really good if you want to move real fast for large jumps. There's just a block diagram. I'm not going to. It uses I2C communication. And this is a little level shifter because the PIC is running at 5 volts and the SI570 is running at 3.3. This is the basic block that you have to send out to it. This is what the PIC has to figure out how to do to command that SI570. And you see there's a bunch of parameters that are look kind of weird, and the programmer's got to set this up. Basically, it is all table driven, except this R freak, which I have to generate, which is a 10-bit integer and a 28-bit fraction. Now we talked about using a high-level language. I did this all in assembler because I challenge you to try to find a routine that'll do this. I had to end up taking a C or a large assembler 32 by 32-bit division apart and running it in binary on paper, first of all, to figure out how this works, and then extending it so I could get the fractional output, like long division when you were kids. Okay, that's what I had to do, and I had to make this thing work in binary. And it comes out now, the output of my division is just perfect to just drop right into these two registers and we're ready to go. So that's what gives it the speed. But if you're trying to find a C routine to do this, good luck. This is what my little daughter card looks like, SI570. This is the schematic of it, just a very simplified version of it to drive it. And that plugs into the daughter card slot here, okay, of a pickle board. This is a little control board that I made. If you don't want to run, when you finally get all the code developed, and you want to move it into a standalone board, this is basically the same circuitry, same everything as the pickle board, but it's in a standalone circuit. Standalone circuit, and you take the PIC out of the pickle board and you drop it in here instead, plug in the LCD, and then you can run it. It's a nice little signal generator. People have been using these all over to run transmitters or receivers. And this was just a couple months ago, the cover picture on QEX here, which was kind of fun. And they're selling these, King sells these. Very quickly to make it into a complete receiver, just a few parts from the SI570. And you can use it in a soft rock type application, with this being a signal generator down here through a couple parts and coming out with audio, and then the PC processes it. And if you also want to use a micro R2 type thing, this is the left half and this is the right half. But once again, it comes into a counter through the SI570, into a Talo mixer, and it comes out the other side, and basically this suppresses one half of the audio, so you come out with single sideband, one side or the other. And also very simple to make it into a transmitter, almost no parts at all. We talked about that before. And, or also a sideband as well. Very simple. Now, wrap it up. A couple years ago, I was driving about 20 miles to work, okay? And as part of this drive, I decided to make use of my time. And I ended up buying an Amazon Kindle to have in my car. It was about a half-hour drive one way and about hour and a half, depending on the traffic and coming back. So I bought a Kindle, and I fixed up a neat little way with duct tape and a rubber band and things so I could hook it onto my steering wheel so I could read while I was going. No, I didn't, folks. Really, I didn't. No, the Kindle has a text-to-speech feature. So you can turn it on in the book, and you can sit it on the seat, and you can have it read to you. It's like books on tape. And in the time, I went through some incredibly good books. I went through all kinds of books on politics and economics and a bunch of religious books, faith issues and things that were fantastic. But I also got into biographies, and I got into a biography of Thomas Edison. Now, Thomas Edison, you think, oh, a long time ago, what would we learn from a guy, Thomas Edison? Well, I'm not going to give you a book report, but basically, I think Thomas Edison had some principles that we can all take to heart and see why, when we do experiments, why we're doing some of the things that Thomas Edison did. You say, man, he was such a brain and everything. He must have just come, it must have just come flying to him. Well, folks, it didn't. So some of the lessons, first of all, just to tie it together, he was an excellent CW operator. He did a lot of CW for the press reports reports back in those days. In fact, he was in the press room when the news of Lincoln being shot was passed. So he could go 35 to 40 words a minute, no problem at all, and he was writing it down by hand. He didn't have a computer, and somebody else had to be able to read that after he was done. And so, phenomenal. He did a lot of experimenting with wireless, even before Marconi. He ended up selling one of his patents to Marconi. He wanted to do work on other parts of it. He didn't think that that was as important, and Marconi bought his patents and went on in that direction. So, but Edison was right in the middle of it. Extreme patience. He would do experiments over and over, and we're going to talk about that in a second here. And insistence on good record keeping. Edison had thousands and thousands of these little notebooks with all the records of his experiments. The only time he'd get irritated is when people didn't keep good records of their experiments. If something failed, he wouldn't worry about it. He would just keep on going. He said, that's one more thing that didn't work. Secret to achievement, hard work based on hard thinking. Now that's what I think we need to apply. That's each one of us, as we're doing our experiments, we're thinking, did it come easy? No. This guy really worked hard. He worked hard, hard, hard. Okay? And one example, okay? When one of his guys was asked, how many times did you have to run an experiment? This was in particular for when he was doing a storage battery, trying to figure out the different kinds of elements to use for the positive and negative. And his assistant said, well, I don't know exactly, but here's the way to look at it. He said, we used to start counting at 1 in the notebook, okay? And we count the experiments, and we count up to 10,000. And we got to 10,000, then we'd start counting back again to 1. And he said that storage battery took us several cycles before we got to the answer that we wanted. Now, how many of us are willing to run that many experiments and keep track of what we did and keep going and not give up? Okay? That's hard work based on hard thinking, okay? It didn't just fall in his lap. He just had the determination to keep on going. And I think that's what the basis of all this is for us. Is that when you get into experiment, find out something you're interested in. Okay? Find out something you want to experiment with. Dig in hard and write it down in a notebook. Okay? Keep track of all the experiments you're doing, and then don't give up. Keep on charging. That's the lesson. There's some references and stuff, but you don't need to